Here we go. Okay. Welcome everyone to part 2 of my presentations about my master's thesis. So today, last time, I'm going to start with a bit of a recap, but just to give you an overview of what I want to talk about today. Last time we discussed the concept of reducing 10H neural networks, as in eliminating units from them to get some kind of minimal representation of their functions. And I promised this time we'd talk about a kind of approximate minimization where you look for, you say, oh, well, what if the parameter is allowed to be a little bit different? Or another way of thinking about it is, what if this parameter is kind of close to a very compressible, very reducible network? And this is going to be the idea of approximate degeneracy or approximate reducibility. And I want to talk all about that today. I think we'll be able to fit in a brief recap of the concept of rank from last time, and an algorithm for computing the rank, which I didn't actually write up last time, but it's a simpler algorithm. It's sort of like a streamlined version of the reduction algorithm we talked about last time, fast reduce. So rank, and then a definition of what I'm going to call parametric approximate rank, which is this relaxation of that concept. And then we can talk about what is computing the parametric approximate rank like? What is that what is the computational character of this object? And I'm not sure if we're going to get to the NP completeness proof today, but I will at least be able to set it up, if not sketch it. So yeah, we'll see how far we get. Okay, so I'll start writing some of that up on the board. So yeah, let me remind you of the setting very briefly. So the setting is these hyperbolic tangent networks that have some number of input units, n input units, connected to some number of hidden units, h hidden units, and some number of output units, m output units, m output. So we have each hidden unit has an incoming weight vector, b, that represents the sort of values from the input units. It has a bias, c. It has an outgoing weight vector, a. And the output units themselves have a bias. And so collectively, this whole bias on the outputs is called the vector d. And so the functions, the parameters look something like w, which is a member of the parameter space wh. So you could write w equals, there'll be a bunch of a's, we're going to put alphabetical order, so a1 through to ah, b1 through to bh, the input vectors, and then the incoming weight vectors for the hidden units is b's, and then the c's are the biases, c1 through to ch, and finally the outgoing weight vector d. So some of these components of this vector that I'm writing out are actually themselves vectors if you have multiple inputs and outputs. But also, I guess you could just consider the case where they're scalars and you have a single input and a single output if you prefer that. Anyway, we end up with the function f of w is equal to, let me attempt to do this in some kind of color coding, d, which is our constant output, plus a contribution from each unit, so from I equals 1 to h, of the outgoing weight vector. So this is a kind of vector output from that unit, its contribution to the vector output of the function, AI, the activation function is 10h. Then we have inside the 10h, the incoming weight vector, the dot product of that and the input. Oh, I guess I should say fw of x, x being our input in n. Anyway, last thing is the bias, ci. So this is this setting. And last time I talked to you about the concept of taking a sum like this and applying some simple rules to basically either eliminate from this sum certain of the units contributions because maybe AI was 0 or BI was 0. And in the case AI is 0, you can just straight up remove that unit. In the case BI is 0, that unit contributes a constant, which you can just fold into D. And the other possibility was that maybe two of these units were kind of proportional because the BI and the CI were equal, and so you just pull together the AIs. Or maybe the BI and the CI are negative of each other, the two units, and then you can use the odd property to make them equal, and then you can pull AI and like negative AJ, where AJ is the other weight vector. So I'm hoping you remember roughly that those conditions of reducibility. And so I showed you an algorithm that takes advantage of those patterns and compresses a parameter to an irreducible, also equivalently a minimal representation or implementation of a particular function. And I'm going to introduce now on the second board a fundamental definition, which is the rank. So let W be a parameter in the parameter space. Then we can define this thing, the rank of W is equal to the minimum, oops, the other way around. The minimum H such that FW is, how should I put this? Is in FH. No, I've got two H's now. Okay, sorry, getting a bit confusing. I'll use R for the rank. Yeah, okay, I'm going to sort of inline a few definitions that I have in my thesis here so that I can get this in one go. So the minimum R such that there exists another parameter in the version of the parameter space with only R units, such that f of W prime is equal to f of W. So you could implement this one function with W prime or with W, but W prime maybe has fewer units. The least number of units that you could use, that's the rank of the parameter that you started with. So the rank is going to be at most H, because you know you can implement this function by definition with H units because you started with an implementation with H units. But maybe some of those units are redundant. You can apply the algorithm and you end up with, you apply the fast reduce algorithm and you end up with maybe only a subset of those units actually left in the reduced version of the parameter. And the number that you end up with would be the rank of the parameter. And so let's talk about an algorithm for computing it. And this will also serve as a way of revising the fast reduce, because an algorithm for computing rank, well, one algorithm, I'm going to write this up and then I'm going to delete it, is you refer to last time and we had this algorithm fast reduce. Do that. So take W prime is equal to fast reduce of W. And this is in, let's say, WR. I'm sort of introducing this variable to my algorithm that is whatever size this parameter happens to be. It's not exactly the dimensionality of the parameter because, but it's the number of units. And so there'll be more parameters than units because each unit has sort of input vectors and output vectors and stuff. But anyway, you can read this off from the parameter if you know the structure. And then anyway, that's the rank. So you return R. Fast reduce is doing a little bit more than you need here in computing W prime. We actually only need the number of units in W prime. So with apologies, I didn't mean for this to be something that stays on the board. I'm going to erase this pseudocode and start again and write out an algorithm that I won't write out the fast reduce algorithm again, but I'll write out this algorithm, and you might be able to remember that it was very similar to this. I'm just going to do the steps. Basically, I'm just going to do the steps from fast reduce that actually involve determining the number of units that we're going to end up with. And I'm going to skip all of the other steps. So, okay, there were 3 passes in this algorithm. There was pass 1, where in fast reduce, this pass was about eliminating the units that had 0 incoming weight. The B value of the units was 0. But actually, in this case, oh yeah, I do need to kind of eliminate them, but it's kind of more about counting them and identifying them. For example, I don't need to know the final outgoing weight. So I'm just going to, in this case, be counting or identifying the units with BI equals 0. And I think in the pseudocode in my thesis, I do it like this. I gets the set of units. Oh yeah, W to start with is in WH again. So the units start, they could be 1 through to H, such that BI is not equal to 0. And so I'm saying which are the units that are actually going to proceed through the fast reduce algorithm. Pass 2, we have to take these units and we have to do this partitioning step where we group together the units that are going to get merged into a single unit. And we're not going to have to actually merge them. We just have to identify how many groups there are almost. So this is the partitioning or merging steps. So put it like this. I'll let the partitions, I am actually going to need the partitions in this case rather than just how many groups, and that'll become clear why in a moment. Pi 1 through to pi k, let's say there are k groups. This is partition I, which is the units that are remaining, by the equivalence relation I equivalent to j if and only if, what would it be? Bi Ci equals plus or minus Bj Cj. So this is these are the cases where we'd be able to merge the units. If either of these is true, then I'm going to consider the units equivalent, and then I'm going to partition I into those equivalence classes, and I'm going to name those pi 1 through to pi k. I do actually need to know the outgoing weights of the merged units. And that's because if that outgoing weight happens to be 0, I can still eliminate that. So for counting purposes, I need to know how many I'm going to eliminate. And so what I don't need to do is compute the final Bi and Ci, or beta and gamma it was called last time, but I need the alphas. So let me do this. For I, sorry, I'll use a different letter now. So for J gets 1 through k. So for each partition, I want to identify what is the final outgoing weight going to be, because if it's 0, I need to not count that. And if it's not 0, I'm going to end up with a unit in my final network, so I'm going to count it. So Aj is going to get the sum over I in pi j, and I'll just put again here plus or minus AI, where, like last time, I'm not going to go into details, but whether or not to use plus or minus, I basically just don't want to put the notation in. Conceptually, it's very simple. If you just got to be consistent. If this was pick one, and if it was positive relative to that, use plus, and if it was negative relative to that, use minus, so that these are kind of consistently as if you were merging into a single unit. depending on which reducibility condition, the positive or the negative you're using. And I've almost run out of room, but I think I can just squeeze it in. For a final pass, very simple. I just want to count how many would be remaining after we eliminate any that have alpha 0. Count alpha j not equal to 0, and return that because that is going to be the rank. So return the cardinality of the set alpha j such that alpha j is not equal to 0. That's not quite right. I guess j, because maybe the alphas are the same. And I don't care if they're the same because the betas and the gammas will be different. So these will be different units. I just want to know how many units are there going to be out of the k that I've got, how many of them are going to stay because they're not eliminated in the final step. Okay, that's what I've got for a recap from last time, and this sets us up for this time with this new concept of a rank that we formally defined this time, a reminiscent algorithm that's simpler than the fast reduced algorithm we did last time, but just does the steps that are necessary in order to actually compute the number that you're going to end up with and doesn't bother to track the other details. But yeah, is otherwise very similar to that algorithm. This algorithm for computing the rank is very important to this, to the next thing we're going to talk about. So I'll pause now for any questions. And I know I've been talking a little fast, so yeah, any questions? I'm happy to spend a bit of time here making sure everyone understands these first elements. Okay, well, let me just plan out the rest of the talk, where we want to go from here. So I'll start by saying that this rank concept, it has all of the issues that we discussed last time about being an idealized measure of how compressible a network is, how many units you really need. Because it works on exact equality, this is the minimal number of units that you're going to need. But if you imagine actually training a neural network in practice, you're going to end up with floating point weights, and maybe they're like actually very close to being similar, but they're not identical in their floating point representation. They're not quite within machine precision, but you know, it's not clear that the precision that the differences that we have between them are actually meaningful, and maybe you would want to combine think about two parameter values as identical, even though they're not quite. We start to want something a little bit relaxed compared to this idealized measure of compressibility. And that's one perspective on the next notion that I'm going to introduce you, which is called the parametric approximate rank. And then after I put up the definition, I'm also going to give you a second interpretation. So let's do that. So the rank was the minimum number of units that you needed to represent a particular function. Now let me attempt to define the parametric approximate rank on the next board. Okay, so we're same setup. Given W in some particular parameter space, WH, I'm going to define, this is a little bit more, this is like let me find the definition in my thesis so that I don't have to think too hard about this. Define the, oh yeah, no, sorry. We're also given a radius. So we need some kind of tolerance within which to consider like two nearby parameter values to be effectively equal or approximately equal or something. And so I'm going to be given a parameter and also a radius. A radius that I'm going to call epsilon, which is just some positive number. Define the parametric approximate rank, which I'm going to write as P rank or prank. Epsilon, it becomes a subscript, and W is the sort of subject of this. It's a property of W, and this is defined as the minimum, missed my min again. of the rank of another parameter, u, where u is close to w in parameter space. I'm going to write it like this. U minus w in the L infinity distance is less than or equal to epsilon. So what this looks like is you've got your parameter space. You have your particular parameter w. You form a uniform distance neighborhood around that of radius epsilon, and uniform distance, L infinity distance. Sorry, I use the uniform distance as the terminology in my thesis, so that's what I'll probably reflexively use when I'm talking, but you'll know this is the L infinity distance. The radius of this is epsilon. You look inside this neighborhood for another parameter, u, that has very low rank, as low rank as possible within this neighborhood. And that becomes the parametric approximate rank of w. So what this definition is saying is we should consider this parameter w. Let's say u has very low rank, like just to be concrete, maybe w is irreducible in a 100 unit architecture. So w has a rank of 100. But maybe it's so close, if you just tweaked the parameters a little bit and moved it over, just perturbed it a little bit to get to this u, maybe u has actually a rank of like 10 out of 100. And maybe that's the lowest in this neighborhood at this tolerance epsilon. Well, then what this definition is saying is that there's a sense in which w is almost a rank 10 parameter. And that's what it means to say it has a parametric approximate rank of 10. If you perturbed it a little bit, it would have a rank of 10. And the definition is what's the best rank, the lowest rank you can get with a perturbation of a fixed maximum size epsilon, according to the L infinity or uniform distance. So that's the definition of parametric approximate rank. Just to finish the picture, I guess I'll say that means this has rank epsilon w equals 10. Okay, any questions about this definition so far? Okay, let's talk about one more interpretation of the parametric approximate rank, which I think I kind of came to articulate so late in my thesis that I didn't find a place to actually write it out in a paragraph somewhere. But there is a point in my thesis where I at least kind of allude to this in my thesis. Another interpretation of the parametric approximate rank is based on another kind of way of looking at the parameter space. So I'm going to draw on the next board the parameter space again. And I'm going to say, I think I used purple on the last board to talk about low rank parameters, rank 10 parameters, to be a little bit more concrete. Maybe there's some part of this parameter space that is rank 10. I'm trying to draw some kind of like measure zero set inside this. Obviously, this is like a very conceptual picture. But anyway, this is rank less than or equal to 10 within W 100 or something. So rank less than or equal to 10. If you then take a uniform distance, maybe be a little bit more dramatic, a uniform distance radius of this entire set, I'm not exactly sure. I should have gone with squares or something, because I'm not exactly sure what all these slanted lines are going to do to the uniform distance of the set. It might not look like rectilinear, for example. Anyway, but yeah, say that this these rectilinear distances are epsilon, then these in this blue dotted region, these are the parameters with the parametric approximate rank epsilon less than or equal to 10. So yeah, this is just you can see by the definition that these definitions are going to be equivalent. You're going to be, another way of saying it is an equivalent definition of the parametric approximate rank. I guess I can write this down, is rank epsilon of W is less than or equal to some particular value if and only if there exists a parameter U with rank of U is less than or equal to R, and the distance between these two is small. U, W infinity is less than or equal to epsilon. So this is not saying too much more than just the definition, but it's another perspective that I think we're going to be able to interpret a computational problem that I say, which is in terms of bounding the rank, in terms of now determining whether or not you're near a bounded rank region. So that's the use of this picture. Okay, that's the definition of parametric approximate rank. So we can turn to discussing computing the parametric approximate rank and how hard or easy that might be. But I'll again pause for questions. Can I get a little bit of feedback if this is sort of clear so far, or if I've kind of lost you guys, because I'm not getting any questions, obviously.
Okay. It's clear to me, but I feel like I've read most of this in your thesis, so I don't want to like answer.
Okay. Okay. I heard someone else say when Dan was saying, and just was it clear or not clear?
It's clear to me as someone who is ill-prepared by very minimal to zero reading of your thesis.
Okay. That sounds like a good, I feel more confident. Thanks, everyone. Okay, so let's move on to computation of parametric approximate rank. And yeah, obviously, if anything is unclear as we go along, you know that you can just pipe up. So yeah, let me talk to you about how you might go about computationally finding these nearby low rank parameters based on the first diagram. The problem of computing the parametric approximate rank, you can view it as kind of trying to find this nearby low rank parameter by tweaking the values in your network. So for example, if you have a network that has yeah, I think some examples would be helpful here. If you have a network that implements a function with 2 units, so I'm not going to write out the parameter, I'm just going to write out the expression of the function. Something like, let's say, tan h of 10x plus 1, I don't know, it doesn't really matter, plus 0.01 tan h of 3x. Okay, so you can see that this is a, you can see that this parameter implementing this function, if you're doing it with 2 parameters, and I'm kind of writing it in the fully expanded form here, these are 2 different units. Neither of these, both of these do contribute to the function, and you can't combine them, and you can't eliminate either of them. But you can see because of this 0.01, we're somehow very close to this second unit not contributing to the function. And if we perturbed this by 0.01 towards 0, so that this became 0, then we would meet a reducibility condition. and we would be able to eliminate this unit. Another example would be if you have two units that are kind of almost have the same weights, and you could almost combine them. So let me look at that. So something like this, 10h of 0.99x plus 10h of 1.01x. Now you can see that there's a couple of ways. So once again, irreducible, because we don't have any identically equal incoming weight vectors. We don't have any zero weight vectors outgoing or incoming, so this is irreducible. But you can see that if we made a small perturbation here of plus 0.01 and here of minus 0.01, then suddenly we'd have 10h of 1x plus 10h of 1x, which would combine to give us 210h of 1x, which is a rank 1 function. So while this was rank 2 initially, it's close to being a rank 1 function. Like the first example, rank 2 initially, close to being a rank 1 function because one of the units could be potentially eliminated. Maybe one more example. This is just, I'll just enumerate these examples here. And one more, I want to show you that you can eliminate both of the units with something like this. Maybe 10h of, okay, yeah, let me do this one a little bit more subtle, but this will make an important point. 1.01 10h of 1.01x plus 0.99 10h of negative 0.99x. So now if we do some perturbations, if we add, if we subtract 0.01 here, we get to 1x. And if we subtract 0.01 here, we get to negative 1x. And we know that is going to allow us to, because of the odd property, combine these units. And if we combine them, you can imagine taking the minus out of the bracket, and then you'll have 1.01 10h x minus 0.99 10h x. That will simplify to a single unit, which is 0.02 10h of x, 1x. This is not, this is rank 1, but it looks like it's very close to being rank 0 because we can almost eliminate this one. I want to say you could consider perturbing one of these. You could consider perturbing this one to be 1.01 or something like that. But actually, you can again kind of split the perturbation, make it even smaller. You can make this. You can subtract 0.01 here, and if you add 0.01 here, then these weights are going to be 1 and 1, and they'll perfectly cancel out. And you won't get 0.02 here, but you'll get 0. And then you can just cancel the whole thing, and you have a rank 0 network. So if you are clever with the way that you tweak the outgoing weights, sometimes you can set it up so that after you combine units, their outgoing weights will add up to 0, and they'll cancel. So these are the kind of ways that you can find yourself near a 0 unit, a low rank parameter, a lower rank parameter that you started with, by kind of tweaking individual parameters in a direction that will set them up to combine or eliminate, or eliminate and combine and then eliminate. Yep. Was there a question?
Oh, I unmuted, and maybe that resulted in some noise. I was just wondering
Yeah,
Yourself.
that's right. Yeah.
Is there a context you have in mind with perturbations, such as training? Like, are you thinking? I know what you say is true, regardless of why weights are being perturbed. But do you sort of have in mind that as you train, you might move through different ranks, kind of thing?
Maybe. I mean, it's far too early to speculate, I would say, what these what effect these to tell a story about moving through different ranks during training. But we can say there's some evidence in papers that I cite in my literature review, for example, that if you are during a gradient descent search, if you're anywhere near a low rank parameter, which, by the way, to refer back to something that we talk about often in this seminar, is kind of like being near a singularity in the information landscape or something like that. Even if you're irreducible, but you're sort of near one of these sort of special points, which is modeled by this perturbation, then the dynamics are going to be affected by the point. So these low rank points, one of the things that happens when you're near a low rank point is that I think we briefly talked about this last time. You can kind of continuously vary the parameter and keep the same function. So there'll kind of be these like flat stretches, these like level sets near the point. So if you're near that, that's like a feature of the gradient landscape as well, because if the function stays the same, then the loss stays the same. So you're going to have these level sets in the loss landscape, and that's an important feature in sort of determining the dynamics of gradient descent nearby. Yeah, and there's probably more that we can say about what effect this might have on the dynamics of gradient descent, but I'm not exactly ready to say it yet. That's one class of things, is that sort of, if I summarize what I kind of stumbled through there, being near to a low rank parameter in parameter space during learning, I think that low rank parameter is going to have some bearing on the dynamics of gradient descent nearby. That's one point. Point two would be, I would like to be able to measure how degenerate a particular parameter is in a practical and non-ideal way. I would be able to say, set some reasonable tolerance that accounts for the fact that there's sort of machine precision issues in adding things up and representing numbers, and there's we don't always train to ideal equality convergence on the data set or the loss or whatever. But I want to be able to say, for this particular parameter that I encountered during gradient descent, maybe it's the final trained parameter that I found, is it a low rank parameter? I'm probably not going to get a very interesting result from computing its rank, because that's too sensitive. But maybe if I compute its approximate rank with this definition, I might be able to say, oh, look, it's nearby to an idealized low rank parameter. There's almost a lot of redundancy in this parameter, and that would be an interesting result to me. So it's two things. It's these low rank parameters being nearby them might be consequential, and understanding how to determine that, how to measure this kind of approximate rank, or how to detect being nearby a low rank parameter, would be experimentally useful.
Thanks.
Any other questions? Okay, so this gives you a flavor for what these kind of perturbations would be like. And so our task now is to come up with some kind of algorithm that is going to find the best perturbations you can do to compress the network as much as possible. It turns out that that is hard computationally. And that's the big sort of result in my thesis, and in particular in chapter 6 of my thesis, which is that computing the parametric approximate rank is NP hard. It's an optimization problem if you view it like we've been doing on this slide, trying to kind of find the perturbation that compresses the network as much as possible and actually compute the rank, the parametric approximate rank, which is, you know, solving this minimum. If you consider it just about bounding the parametric approximate rank, that's a decision problem. So that's the problem of, I'll write up this problem. Computational problem. Given W and epsilon, and a particular purported or sort of prospective, that's the word, prospective rank bound is the parametric approximate rank at radius epsilon of W less than or equal to R. This is a decision problem, and one of the theorems in my thesis is that this problem is NP complete. So bounding it is kind of part of the way to computing it. If you can compute it, then you can figure out the bound easily. But you might also just be interested in a bound because it kind of gives you partial information about the quantity, and you might not need a precise the precise value. You might just need to know whether or not it's like lower than a certain threshold. Another way of looking at this, though, it goes back to our second interpretation of the parametric approximate rank. This problem, computing whether the parametric approximate rank is less than or equal to R, is the same as, by that equivalence, detecting whether or not you're within some, well, radius epsilon of the bounded rank region of the parameter space with rank R or less. So the fact that computing this, detecting whether or not you're near this bounded rank region is NP complete as a computational problem, that sort of says something about how the shape of this bounded rank region is kind of like intricate, computationally tricky or complex, or there are at least parts of it that are, you know, computationally complex. So that's the result of this that I'd like to convince you of with today, if not also one more session, because this was sort of the most substantial proof in my thesis. Let's talk about what it would actually be like to compute this thing, this parametric approximate rank, finding these perturbations. Why does it get so hard? Why can't an easy solution do it, or something like that? So I'm going to go to another example, but I'm going to be a little bit more visual this time and show you sort of a representation that I use for thinking about this. Imagine now that our setting is n equals 1 and m equals 1. If you remember, these are our number of input units and output units, respectively. So these networks look something like this. We still have some number of hidden units, but there's only one input unit and one output unit, and I have h hidden units. And each of these hidden units has a bias as well, so we better not forget about that. They kind of have two input parameters and one output parameter, which is the AI, and the inputs are the BI and the CI. So the problem of finding these perturbations, the reason that I'm in this setting is because now imagine, I will write this out. So W's look like something like this. it's the same as I wrote out before, but now these are actually scalars now. AH, B1 to BH. Before BI and AI might have been vectors, but now they're definitely, and there's D, they're definitely scalars because there's only one, well, the bias was always a scalar, but there's only one input unit, so there's only one input weight, and there's only one output unit, so there's only one output weight for each hidden unit. So now I can take I can take these input units and I can, input weights, and I can make an axis, B, and I can take these biases and I can make another axis, C, and for each unit, I can draw it as a point, and that would represent that B1, C1 is the kind of input parameter of this particular unit, hidden unit 1. So, for example, this would represent 10H B1X plus C1 as a unit being represented as a point in the plane. And I get a point cloud if I do all of the units, all H of them. So I'm going to add some other points here, maybe in a slightly different color. So the problem of, let's say, figuring out if we can do some perturbations to B1 and C1 to make them equal to another, maybe B3 and C3 or something like that, is going to be about, it's like a geometric problem in the plane. It's like a clustering problem. For example, maybe we can perturb this B1 point and this point here, we can perturb them up to here. If you look at this, maybe we haven't changed C1 much, but we change B1 a little bit, we increase it. And maybe for this other point, we decrease the B value and increase the C value a little bit. And we bring them both to this orange point. And if we did that, then we would be able to merge these two units. And maybe similarly, this little triangle over here of 3, we can merge those all into here. And maybe these ones we can just reach if we go with whatever epsilon we have. We can just reach if we bring them over together. And maybe we can reach these ones together too. And maybe it doesn't matter where we move this one. There's nothing around, so we might as well not even bother perturbing it. We'll just leave it where it is. But now, I guess I'll put a point here, orange. Now we've got 1, 2, 3, 4, 5 units instead of however many we started with. I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, instead of 10 units, we've got it down to 5 units. And the important thing from this picture is, can you see that this kind of geometric perspective on perturbing the units individually corresponds to some perturbation of the parameter W that will lead us to a lower rank nearby parameter in parameter space if these individual perturbations are less than epsilon in each direction. That's kind of the point of this diagram. Yeah, I'll pause for questions. And also, I'm asking you the question of, does this make sense?
Yes.
Okay, cool. So,
maybe I'll ask
a
question.
Yeah, question.
So if I merge together those 2 units you started with, then the single unit that remains sort of has the sum of the outgoing weights, I guess, as its outgoing weight. So
that's right.
Isn't that quite large compared to, I mean, that somehow is a big movement in the outgoing weight or something like that. But it's like you could think about that as somehow being further away, but that's not the point. But why?
Yeah, okay, good question. So let's come back to the first examples that I drew and have a look at the second example here. This is what happened here. We made a small change to the incoming weights of these 2 units, and we ended up with something that effectively has a vastly different outgoing weight. However, this change is an illusion. This is after we compress. This version here is the parameter that is nearby and low rank. Does that make sense? Cool. So yeah, it's a distinction between compressibility and compression or something like that. Remember that rank is about how much you could compress if you wanted to, and that's what we're measuring. And even if compression would involve a large change to the weights, which it probably, as you point out, will involve these large changes, compressibility doesn't need any changes. You don't need to actually affect the changes to have a low rank. Good question. Any others? Okay. I'll this brings me to the kind of I'm in my thesis. What I do is I set up this this problem as a clustering problem like this. With specific rules, you have to be a little bit careful about how much of a perturbation you allow these orange arrows, how large you allow them to be in each dimension. Obviously, it's based on the epsilon. And you have to be a little bit careful about some other things, but you can basically invent a new abstract problem that is about take a set of points in the plane. How many kind of groups do you need to group them all like this? In this case, the answer would be 5, and you started with 10 points. That abstract problem, which I call uniform point covering, or it has a couple of other names because I give a couple of other perspectives on it in the thesis. That abstract problem is one that is sort of involves an intricate proof to show you can embed a satisfiability problem into the plane, and I'm excited to tell you all about that. But that is like a 2-step reduction. I define this abstract problem and I relate that to satisfiability. It remains to technically relate this abstract problem to the problem of computing the parametric approximate rank, because from what I've told you so far, this is one way that you could think of computing the parametric approximate rank or bounding it. But maybe there's some other way. You don't have to look at the plane. Maybe there's some other clever way that you could do this without getting away without having to do what I'm going to show you later is a quite hard problem in the plane. So what I need to do is show you that this problem here that we're looking at is basically just as hard as computing the parametric approximate rank. They're kind of equivalently difficult. Actually, I think computing the parametric approximate rank might be sort of a little bit harder because, well, I'll tell you why now. So imagine if we had some points over here, we'd suddenly have to start worrying about the merging units because they have negative weights. And if you imagine that this weight here, let's see, this unit here, if I was to negate it, I may end up here somewhere, and maybe I would actually be able to merge it into a group with these 3 together. So it's you have to worry about the signs and the absolute values of your components. Also, if anything has a b value of 0, if anything is anywhere on this axis, or actually because we're allowed to do perturbations anywhere near it, you could just perturb it to the axis. And then you would be able to eliminate that unit. It wouldn't really count as a group. So anyway, the point is things get a little bit more complicated when you consider all of the different reducibility conditions, the different ways that you compress your parameter. what we're going to do when we set up a problem, one way of looking at it is when we set up a satisfiability problem, I'm going to show that basically if you work a certain amount away from the axes, if you put a distance of 2 epsilon here, and you never go into the other quadrants either, and you do all of your work in sort of well into the positive quadrant here, then you don't have to worry about any of these issues. And the only way that you can have parameter reduction is by merging. And so that more tightly connects the problems, this abstract problem of clustering and the reducibility or approximate reducibility problem. That's one thing. And so this working in the positive quadrant, well into the positive quadrant, deals with the other conditions. And one more thing. When you do merge units, it's also possible that suddenly the outgoing unit, the outgoing weight combined will cancel out. And then you kind of get to count this cluster for free or something. It doesn't add 1 to your total, to the rank of the parameter that you found. That's also a nuisance, kind of computationally. It's not easy to represent that in the clustering problem, the abstract problem. So to show that we don't have to worry about that, we work with we work with neural network parameters where all of the AI values are themselves quite positive. So these are all also greater than or equal to 2 epsilon. The constraint I talked about before is that these are all greater than or equal to 2 epsilon. If we work with these parameters, then you're only ever doing positive merging because all of your weights are actually positive. And when you do positive merging, you're adding together the outgoing weights. You never do AI minus AJ because you only get to use that combination if you had something negative and something positive merging together. So these, the outgoing weights are always, they stay above 2 epsilon. They stay far above 2 epsilon. If you have many weights, you end up with 2 epsilon times the number of weights as your outgoing weight. And so you could never perturb that to 0. And so we basically, by working in this part of the parameter space, we make sure that this merging that I'm talking about here with examples, that's the only kind of perturbation you can use to reduce the rank of the parameter. So that's the connection. And I have a section in my thesis that basically proves that if you use these tricks, you can reduce, let me make sure I get this the right way around. You can reduce this abstract point clustering problem to computing a bound on the parametric approximate rank, which means if you could compute a bound on the parametric approximate rank of an arbitrary parameter, you must be able to handle it in these cases. These cases are enough to handle any abstract clustering problem because you can always just shift the clustering problem into the positive quadrant by adding enough to each of the points. Okay. So therefore, all that matters, the upshot of all this is that all that matters is this abstract point clustering problem. Let me see if I can summarize that or write that down somehow. But in the meantime, any questions? This is any questions?
Not from me, but I think as you're talking through this, another bonus that the audience might derive from the talk is if you mention places where there are things to be done, maybe some of them you will do, but maybe also you'd be willing to open up the floor to people who might want to take a shot at some of these open problems.
Yeah, sure. There'll be more later, but one of them is that, so an ongoing sort of task, a task that comes out of this thesis is to generalize the setting from 10H networks to, for example, ReLU networks would be an obvious next step. ReLU networks have different reducibility conditions. So you go back to the start and you redo the reduction algorithm and everything with different reducibility conditions. That still needs to be done. When you get to this point, you see that in this reduction, I've kind of said, okay, look, as long as we work in the positive quadrant, everything will be okay. But that's because of the particular symmetries or reducibility conditions that we're trying to avoid. We're trying to kind of focus on the merging reducibility condition. And for ReLU, there's different types of, like, instead of being an odd function, it has a positive scaling symmetry. ReLU does. So there's like a different type of thing you have to look out for instead of this mirror image from the negative quadrant stuff. So it's an open question how to, or whether it's possible to use a similar reduction in the ReLU case based on the unique reducibility conditions that you get when you study networks with the ReLU function. Is there anything else that you had in mind, Dan?
No, not exactly. I feel like it should be something we keep in mind that, of course, some of the people here are students and maybe wanting to work on a problem for their thesis or whatever, but also among the people here who are not students, it should be stated more openly that, these are works in progress that people are welcome to try and contribute to, and we're happy to help them. I would think that would extend to you as well.
Yeah, absolutely. Cool. I will then use, so at this point, the talk is not really planned out. So I got to think a little bit about what is next, but this reminds me of something that I wanted to say eventually that I think I'll turn to that next as a bit of a break from what we've been discussing, but it relates to this. It's like an open opportunity to take a next step. Anyway, let me just finish what I was writing here. So yeah, like I said, not super prepared for this talk, but just kind of improvising. What I've discovered is that what I want to tell you with this board is that the problem of bounding the parametric approximate rank is really about this abstract, the core part is this abstract point clustering problem. If you can solve this abstract point clustering problem, that means you can compute the parametric approximate rank for these certain types of parameters that are sort of in the right part of the positive quadrant, like this. The point cloud is in the positive quadrant. That's useful. I mean, if it doesn't help you with parameters that are elsewhere, unfortunately, but this is the right direction that we need from a computational complexity point of view, because what it means is, I'll use another board. This is important. So let me call some different problems. I'll introduce some names for some different problems. We've got satisfiability, often abbreviated to SAT, SAT, Boolean satisfiability. This is the problem of taking a Boolean logic formula and with a certain number of variables and everything, and determining whether or not it is satisfiable, whether or not there's an assignment of values to variables that makes the whole formula evaluate to true. And this is the classical result in computational complexity theory, that this is a hard problem. We don't know how to solve it in polynomial time. We don't know if it's possible to solve it in polynomial time. And moreover, if we did, it would somehow mean that because this problem is so fundamental to polynomial or polynomial computation, if we could somehow solve this problem in polynomial time, we could solve a whole class of problems that we don't know how to solve. We would suddenly be able to solve them in polynomial time too. And that's because this is an NP-complete problem. It's the prototypical NP-complete problem. Okay, so that's one problem. Another problem I said I called it uniform point covering, UPC. This is the abstract point clustering problem. That I just talked about briefly. I sketched this briefly, but a more formal introduction I'll have to do next, or next time, depending on how we go for time. And a third problem is computing or bounding the parametric approximate rank, PAR. This is to bound the rank of a particular epsilon and a particular W. So what I've said is that if you can solve UPC, then you can solve PAR in certain cases when the parameter W happens to be so far in the positive quadrant that none of these other types of perturbations have any hope of reducing your parameter. That's not useful if you want to solve PAR, because there are all these other parameters we need to care about. But it is useful if you want to show that it's really hard to solve PAR, because what we've got is that if you can solve, sorry, I'm getting some lag, so I'm going to have to slow down a little bit with my writing. If you can solve PAR, then you can solve UPC. I don't know if I've made this clear yet. This is related to what I was talking about on the previous slide. And so this is what I've said so far is if you can solve UPC in the positive, sorry, if you can solve UPC, then you can solve PAR in the positive quadrant. But because you can take any UPC instance and translate it into the positive quadrant, then if you can solve PAR, that includes being able to solve it in the positive quadrant for those parameters. And that gives you a solution to those UPC instances, which you can then translate to anywhere in the plane. So if you can solve PAR, you can solve UPC. And that means that if solving UPC is hard, where hard means like NP complete or some computational complexity statement, then so is solving PAR. You can think of this as a kind of contrapositive. So the first line here is if you can solve PAR, then you can solve UPC. You can think of it as sort of informally as like, well, if you can't solve UPC, then you mustn't be able to solve PAR either. But you know, hardness or you can't solve or whatever is like a that's a very informal way to discuss some very technical topics in computational complexity theory that I will proceed to get into. So this is, so I've also put SAT up here. In my thesis, I prove this here, which gives us the next line. I also show that if you can solve UPC, then you can solve SAT. If you put these together, that means that if you can solve PAR, you can solve UPC, which means you can solve SAT. So if you can solve PAR, you can solve SAT. And then you get if solving SAT is hard, then solving UPC is hard, which means solving PAR is hard. So solving UPC is hard. And if you put all of these together, you get solving PAR is hard, because solving SAT is known to be hard. So just to be clear, these things that I'm circling in red, that's sort of two different sections in my thesis. I prove each of these. The contrapositive of those is these things. And put that together, and you get, with the fact that solving SAT is NP complete, which was proved in the 70s, you get that solving PAR is NP complete. So that's the structure of my chapter 6. So let me see. I'm going to start wrapping up, and there's also going to be time for discussion. But yeah, I'm going to need definitely another session to go into these proofs. But just to maybe summarize, if you can solve PAR, you can solve UPC. This one here, this we've just kind of briefly talked about. I haven't drawn any diagrams to kind of explain this. I've just talked about how you can translate points and used words. If you want, I can do this again in more detail. The big proof is the link between UPC and SAT. And this one's also, I think, a little bit more fun than the PAR one, that other step, because it involves kind of building circuits with points in the plane and thinking about the different ways of clustering them and how that relates to the satisfiability of the formula. And so this is the kind of fun complexity proof that is like a bit of a puzzle, and I enjoyed doing this part of the mathematical work, and I'm happy to also present it because it's kind of fun, but is more substantial, like more complicated, and will take as more steps. It will take longer to explain. This we'd have to talk about next time. The orange one, I could go over it again in more detail now. I could attempt to do what I've kind of verbally sketched out. I could attempt to do that on blackboards now or next time. Yeah, any questions or thoughts on that?
Yeah, sounds worth sketching now. If there's, it seems like at some level it could be done in the next 15 minutes, and then the entire next time could be spent on the first.
Yeah. Okay. I think that's right. Yeah. Maybe actually I will maybe overrule that and say one this thing I mentioned before that I thought of to mention. Maybe that's worth spending a few minutes on and then wrapping up. Okay, so yeah, next time we'll do these proofs that I've given you a bit of a flavor of, or verbally sketched the orange one today, and we'll go into detail on the purple one, which I believe was also the subject of a much earlier talk sketched then. But we'll go through that all from scratch and formally, and I'll prepare to present it in a sensible order and stuff. What at that point we will have proved is that computing this bound is NP complete. I want to tell you now about, I'll return to this second board on this lot of 4 because it fits here. This PAR problem, this is the computational problem PAR. And the result is this is NP complete. So when you show that a problem is NP complete, it doesn't mean that all hope is lost. So this is related to kind of future work as well. Even with Boolean satisfiability, there are many instances of satisfiability, many examples of Boolean formulas where it's actually quite straightforward to find a satisfying assignment. And for certain classes of formulas, you can do this in polynomial time. And there are others that are out there that are actually kind of tricky, and they make you consider a lot of different possibilities and do some backtracking. And it's a hard combinatorial problem. You have to consider so many different possible assignments that, and you can't kind of avoid it because there are like these long range dependencies between what you decide to assign this variable versus another variable a long way away in the formula and stuff. But not all formulas are like that. Some are easy. And in this case of PAR, some bounds are going to be easy to compute. As a bit of a silly example, yeah, what I'm going to do here is make maybe some special cases. As a silly example, if you want to determine if with R equals H, so if you want to determine is the parametric approximate rank of W less than or equal to H, where remember W is in WH. Well, all of the parameters in this epsilon L infinity neighborhood of W have rank at most H, because the fact that they're in this parameter space means you can implement those functions with H units. So this requires no time to tell you that this is always true. That's not so interesting. One that's a little bit more interesting, I think, is this one. And I didn't actually get time to sort of realize this just after submitting my thesis. And this may not always be true. So is the parametric approximate rank of your parameter less than or equal to H minus 1? In other words, so H minus 1 corresponds to the reducible parameters compared to the irreducible parameters. These are the the networks for which at least one unit can be removed. It's not always the case. There are some for this. It's not trivial like the one above. There are some networks for which, if you do some perturbations, at least one unit can be removed. And there are some networks for which, no matter what perturbation you do within a given epsilon, no unit can be removed. But you can figure this out in polynomial time. Because you don't need to worry about sort of being optimal if you only need one example of a unit. You need to find one unit that you can merge with another unit or you can eliminate. You don't need to worry about making a wrong decision because you decided to merge these two units together, but if you had have merged a different two units together, you would have found an even lower rank parameter in that direction. Because as soon as you've decided to merge two units together, you're done. You've found an answer. And you can, basically, if you exhaustively check all of the reducibility conditions, as in for each of the units, is the A value or B value near 0? If the answer is yes, then perturb it to 0, done. And then for each pair of units, are they kind of within epsilon of being mergeable? And if they are, merge them, done. And if none of these things come up, give you an opportunity to reduce, then it's clear to see that there's no way to perturb it to reduce, because you in order to reduce the parameter, you need to operate by these local reducibility conditions. You need to make these a sequence of these reductions. So this case is polynomial time. Because you just have to check each of the reducibility conditions. What this means is, so the NP completeness result in general means that, okay, maybe if you want to determine if the parametric approximate rank is less than half of H or something like that, that's going to be harder, because then you have to make sort of smart decisions with your merging and your eliminating. And I'll prove, I guess, next time that that it's unknown whether or not there's a polynomial time algorithm for that, because it depends on P equals NP. But so that means that it's sort of hard to measure parametric approximate rank. And if you wanted to run an experiment where you trained a neural network and then asked, does it have low rank, that would be difficult to determine, because, well, it's not clear that it, maybe it sort of obviously has low rank, but in general, that's going to be a hard question to answer. But this question, this lets you run an experiment and say, does it have full rank or not, approximately? Does it have, is it near a parameter that is at least a little bit reducible? That should be easy. And I think you could run an experiment today. You don't need any algorithmic innovation to be able to compute or approximate parametric approximate rank in order to run an experiment today and just check, are the neural networks that we get nearly reducible? So that is something that is kind of exciting, because I think this would be an obvious first step to do to kind of find these reducible neural networks in the kind of among the neural networks that we learn from data. And if we find that they're a little bit reducible, then the question becomes, well, how reducible are they? And we can work on that. We can work on developing algorithms for approximating parametric approximate rank, and we can make progress on that in the future. But this would be a sort of a first step. And also it would tell us, well, maybe they're not even nearly reducible, and then we don't need to bother with all the parametric approximate rank stuff. So yeah, I think that would be an interesting experiment to run, and we have the theory for it already.
That's interesting. I might have missed the way you stated it, but I guess you have to say this rather carefully. Otherwise, it looks like you could just iterate this process, which isn't really true, because once you've merged one of those units, you might have gone away from the original W by epsilon, and then that new thing, if you try and reduce it further, you'll be not actually solving the original problem anymore. You can't actually iterate this step, right?
That's right. Yeah, the problem is, like you said, so and
also, if you iterate it down the line, you might make the wrong choices at the beginning, and you might iterate like 5 times and say you can't go below 5, but you made the wrong choice at the first one. So
yeah, that's right. If you sort of approach this problem, remember the slow reduce algorithm from last time. Look for a reducibility condition, but in this case, actually like some kind of approximate reducibility condition, like b is almost 0 instead of b is equal to 0. Look for an approximate irreducible condition, reducibility condition. Take advantage of it, and then move on to the next one in some kind of greedy approach where you just arbitrarily choose which one to use. Then it depends on what order you do these in. So you should even measure, you can even measure like, have I gone in total further than epsilon away? And so you make sure you don't get some kind of like weird wrong answer by always moving a little bit away and eventually being more than epsilon away from your original parameter. You can easily keep track of that, but Edmund's point is the important point. It suddenly depends how far you can go down this road depends on what order you take the reductions in. I think I can give you an example of this. Yeah, can I give you an example of this?
So I guess augment your original example that can reduce down from 2 to 0, and then get another one, and then make the choice to merge the other one, and then suddenly can't get below 1.
You mean back on this board?
Yeah, back on the third example.
The first
so add another node that is 0.98, I guess. And then merge the other 2, and then suddenly the merged node is more than 0.01 away from the first node, and you can't merge anymore. Oh wait.
Yeah,
that's I guess you need another example, another node too. Nope. But,
put it like this. I think if you, so you might realize that No, yeah, the 9.8 has to be in here somewhere. I'm going to put 0.97 here. So you have a choice to either add or subtract 0.01 here. Yeah, maybe if I make this, instead of anywhere near 1, make it just 2, so it's, really far away. You can choose basically to merge these two or to merge these two. But you can't do both. If you move this towards 0.97 or negative 0.97, and you move this, make them both plus or minus 0.98, then you can merge these two units, the second and the third unit, and then the output weights don't cancel. So you end up with rank 2 because you have your first unit and this merged second unit. But if you choose to move this towards 1 and this towards 1, and then you merge these two, and then you can do the thing with the output weights, and then they cancel out, and you end up with no unit out of these two and just the third unit. So you end up with rank 1. So it's rank 2 versus 1, depending on which perturbations you decide to make. And that is a simple example, sort of deciding which way. If you view this as points, by the way, all of these have c equals to 0. And if I just do the odd thing to make this positive, so it's a bit easier, all of these has c equal to 0, and so it's about the b value. So they're on the x-axis in our plot that we had on the other diagram. Put aside the fact that we were talking about being in the quadrant, it doesn't matter. You have 1 here. Then you have your points. You have 1.01, 0.99, and 0.97. And let's say our tolerance is 0.01, so that you could choose to cluster these two and leave this one alone, in which case you'll end up with rank 2. Or you could choose to cluster these two and leave this one alone, and this cluster will happen to magically vanish because of the A values. But you couldn't necessarily have foreseen that short of sort of checking all the possibilities. That's why this becomes a combinatorial problem. Does that make sense?
Yep.
Okay, cool. Well, I'm happy to call it there. And whenever we decide is the appropriate week to resume, I'll prepare to explain these actual reductions, and I'll give a bit of a primer on computational complexity theory, enough to understand the proofs and the statement of the NP completeness result. So I think I'm not exactly sure if everyone's familiar with that stuff from theoretical computer science. Yeah.
Great. Thanks a lot, Matt. Are there any questions for Matt? And then we should have a brief discussion about scheduling the talks in the remaining weeks of the year. But questions for Matt first.
I do have a question. So it's about the choice of the uniform norm, the L-infinity norm. I was just thinking whether or not there is, so two parts to the question. One is, what is the consequences if we choose, say, the Euclidean norm? Because, if, for example, in your third example, so in the Euclidean norm, every time you want to change B or C, you kind of can only choose one, because you choose more. So in the uniform norm, you get a lot of the smaller ones and not ignore them. And this is, I guess, more important in higher dimensions, because there's a ton more volume to the uniform norm.
Yes.
Q.
Right.
But then when you formulate things in terms of the point covering, it seems like it doesn't really matter what the norm is. Like the data input to that problem is just all the pairwise point distance, right? So it doesn't matter what that is. So basically, I'm asking whether or not this, if you have thought about this.
Yeah. Okay. Good question. So yeah, the you've basically summarized my thought process on the choice on this slide when it comes to sort of thinking about the perturbations in the network. It was, I guess, computational convenience to choose the uniform norm, because it suddenly means you don't have to have this global account of how much you're allowed to vary the parameters. You can just get away with, for each parameter, deciding whether or not to vary it up to some fixed maximum amount in either direction for each value. That I hoped initially would make it easier to do the optimization before I knew this was an NP-complete problem. And it also turned out to make it, I think, easier to prove that it's NP-complete, because in this step where you translate this into the plane over here, the fact that this is uniform norm and allows you to kind of treat each dimension's variation independently up to this maximum means that each of these points, you can think of moving them in its own uniform neighborhood without worrying about how much you're moving the other points. And so that vastly simplifies the problem that we're dealing with, the abstract problem, which made it easier to analyze and computationally and prove that it's NP complete. So I'd say it's computational convenience, initially hoping that it would be even easier to actually compute the parametric approximate rank. In the end, turned out to make it easier to prove that even in this case, it's hard. I don't know for sure that if you change to a different norm, you would get the same result, the same NP completeness result, but it seems like you would go through a lot more effort and then you would probably get the same result. It would still be high. It wouldn't make it computationally easier, would be my guess. That's for the first part of your question.
Yep.
For the second part, which was, what about this abstract computational problem? What happens if you play around with that, with the choice of uniform norm now? Is that your second part?
Actually, that was like part 1.5, but gone.
Oh, okay. Oh, well, okay. Then to finish answering your first part of your question, yeah. So this problem, this abstract problem, uniform point clustering, you could say Euclidean point clustering has actually already been studied in the literature. There was a thesis that I found where someone, in the course of doing something completely different, but anyway, they defined this problem. But instead of talking about, well, I haven't formally defined this problem, but I hope from the example we've gone through, you get the idea. It's basically you've got this point cloud, and you want to try and find nearby points, each within a kind of small square, because we're using uniform distance. You want to find points. I drew that square wrong because I want this orange point to be included. You find orange points that are nearby, a small number of orange points that are nearby to as many of the gray points as possible. And where these blue boxes have a fixed epsilon radius, and the radius, they're uniform neighborhoods. So Superwit studied this problem, but for circular neighborhoods or Euclidean distance, and found that was NP complete. And my result is very similar. My proof is sort of similar, but yeah, it's the same computational difficulty. It's this. I'm also doing it based on a reduction from SAT. So it's a very similar result. And this other problem, you also asked about. You said something about the data of this problem. Is it really about the pairwise distances between the points? And I think sort of yes. It sort of matters that they're square neighborhoods, and you're talking about uniform distances, because what that does is it defines the kind of pairwise relationships that are possible. For example, there might be certain arrangements of pairwise distances that actually can't be embedded in the plane using uniform distance to generate them. I'm actually not sure if you end up with, if the set of possible point arrangements or set of possible pairwise distances is the same, whether or not you use uniform distance or Euclidean distance? That's an open question for me, although I'm not 100% sure that it hasn't been answered somewhere in the literature.
Right. Yeah, I'm sure the solution, if you give it a different norm, in other words, give it a different distance matrix between all endpoints, it will have a different solutions. But I think, like, I'm just drawing parallel to all the clustering algorithms out there that doesn't need you to specify a distance function. Just give it the pairwise matrix, pairwise distance matrix, and
right.
work from there.
So the way that I know these clustering algorithms is as like graph clustering algorithms, where you think about the points as nodes of a graph, and you think about the distances as their edge weights, and then you try and find, so that's right. So I guess my question is, I'm not sure whether the set of graphs that you can build in this way via the by the uniform distance is the same as the set of graphs that you can build using Euclidean distances. That's unclear to me. Was there anything else?
Yeah, there was another question, but it's I don't know whether or not it's relevant, but just maybe more of a comment, which is using this maximum distance. So if I have like 1,000,000 nodes, then in theory, I can add 0.01 to every, how many of 1,000,000 node that translate to something like 4 million parameters, if it is n equal to 1, m equal 1.
3 million, yeah.
So basically, I made millions of changes, but in principle, that's still 0.01 away. So that's still within the allowed changes. But my worry is that completely changes the output, the function, right? And I'm just wondering. I think this might have might have thought of this, but like, what is that within this epsilon ball, as in epsilon hypercube? It sounds like the function space distance can be very large.
Yeah, potentially. That's a good point. That's a very good point. In the appendix A of my thesis, I found a result. I studied this. I sort of studied what is the relationship between these uniform neighborhoods in parameter space and neighborhoods in function space of the functions that those parameters implement using L2 distance for some input measure. And I found a relationship. I've at least quantified the relationship, and it does depend on the dimensions, like the number of hidden units.
But that intuition just can't be right. I mean, the topology is the same whether you use L infinity or L2, and the map from parameters to functions is continuous. So
yeah, that's right. So I guess what I'm saying is, for a small enough epsilon, you do get a certain delta in function space because of that continuity, and I've quantified it. And I guess the question is, is that continuous but very steep? Maybe, and it is steeper for larger for larger numbers of hidden units because of what Edmund
is
was
that
saying.
the Lipschitz constant or something like that? And that constant depends on the dimension d. So even though it is continuous, it would be very big. Okay.
Yeah. So I would say that it's the Lipschitz constant of the structure function map, which is the map from parameters to functions that they implement. Right. And it is, well, at least according to the uniform distance in the parameter space. And that constant depends. I've bounded that constant in Appendix A in a way that depends on H.
Okay. Yep. Thanks for that. I will check it out.